So we have another problem here. We have a meter stick, uniform meter stick, pivoted to rotate about a horizontal axle through the 10 centimeter mark on the stick. The stick is released from rest in a horizontal position. Assuming no friction between the stick and the axle, determine the angular speed of the meter stick when it is vertical. Treat the meter stick as a thin rod. All right, so let's make sure this makes sense. So we have a meter stick. It's going to start horizontal. And it's rotating about a horizontal axle through the 10 centimeter mark. So the rotation axis we can think of as coming out of the screen and into the screen at this point, at this 10 centimeter mark. This is the rotation axis. So I'm not particularly great at drawing three-dimensionally, but I'll take a stab at it. So this dotted line represents the rotation axis, and then going through the meter stick at the 10 centimeter mark, when I release it, I know the force of gravity is acting in the exact center of the meter stick, and so I know gravity will create a torque that causes this meter stick to rotate downwards. The question wants us to find the angular speed of this meter stick when it is vertical. So down here, what is omega is what they're asking. So it rotates downwards. At the moment the meter stick is swinging through this vertical orientation, what is its angular speed? Now, we know the force of gravity is applying a torque. There is a lever arm. The lever arm points from the rotation axis out to the force. So initially, the torque is that lever arm, which would be 40 centimeters, so 0.4 meters. That's because the mg is acting at the 50 centimeter mark, because this is a uniform meter stick. The rotation axis is at the 10 centimeter mark. So the distance between the rotation axis and this force is 40 centimeters. The torque would be R times mg. The angle between them is 90. They're already perpendicular. So this will be the biggest the torque value ends up being. Now keep in mind, as the meter stick rotates, this R is changing direction, but mg is not. This angle is changing. So the torque is going to still be 0.4 meters times mg, but the angle between those two is changing with time. So we could technically say the net torque is I alpha. That is a true statement. But this net torque is changing, which means this angular acceleration will also be changing, which means we cannot use the kinematic equations. The big three, we cannot use those because the angular acceleration is not constant. So because I'm trying to relate some sort of initial height to a final speed, conservation of energy, those should work. And it will work, actually. We can totally say that initially the potential energy is going to turn into, finally, at this lowest moment, kinetic energy. Now, we can say that as long as we're saying the lowest point of the center of mass specifically is y equals 0. So y initial is going to be how high above that lowest point the center of mass is located initially. So again, when we talk about potential energy with gravity, the Y value specifically needs to zoom in and look at where the center of mass is. So that's because that's where we're treating the force of gravity as acting. So zooming in, Y initial is actually the distance between the center of mass. Initially, the center of mass is in line with the rotation axis. Finally, the center of mass is directly below the rotation axis. So the initial Y is the 40 centimeters or 0.4 meters, the distance from the center of mass to the rotation axis. Now, finally, remember we have two types of kinetic energy now. We have translational kinetic energy and rotational. In this particular case, as the meter stick is rotating around this lowest point, the kinetic energy is only rotational. And that's because this meter stick is rotating about a fixed rotation axis. The rotation axis isn't going anywhere. So all this meter stick is doing is rotating around an axis. It's not rolling along a surface. And that's why we only have the rotational kinetic energy. And so our fundamental equation we're going to solve is mgy equaling 1/2 I omega squared. And that omega is what we are looking for. Now, we don't know the mass of the meter stick. We do know the Y initial. We know that's 0.4 meters. But we also need I, the moment of inertia. If you go look at the table in the test notes or in the book, there are two I's for a thin rod. That's what this problem tells us to treat the meter stick as. One of them is 1/12 ml squared. The other one is 1/3 ml squared. Now, if you're looking at the table in the book, it shows you the picture of the rotation axis. That's the wrong one. If you look in the table in the test notes, the 1/12 ml squared, it says about its center. So I'm going to put sub cm. That's the moment of inertia of a thin rod that is rotating around an axis that goes through its center of mass. The 1/3 ml squared is the I for a thin rod rotating around its end. Now, this particular problem, we don't have either one, right? Our rotation axis is at the 10 centimeter mark. That's neither the end nor the center of mass, which means we need a different way to find I. This is considered an I nu. If you remember the parallel axis theorem, this new axis is parallel to the one that goes through the center. Parallel axis theorem tells us that I nu is equal to I center of mass plus md squared, where d is the distance between the center of mass and the new axis. So the 0.4 meters, the 40 centimeters. I center of mass from the table is 1/12 ml squared. D is 40 centimeters. Now, I don't know the mass, but that's okay. I'm going to factor it out. L is just 1. This is a meter stick, so it's a meter long. The moment of inertia around this new axis, I'm just going to figure out the number in parentheses. I'm getting 0.2433. And then this is in terms of m, because the moment of inertia does technically depend upon m. I don't happen to have the value, but that's okay. I'm going to plug this in for I in our conservation of energy equation. When I do that, I now see that I have an m on both sides of the equation, so I can cancel that out. So omega, I'm going to bring the 2 over, divide by that 0.2433. We know G is 9.8. Y of the center of mass, as we mentioned, the center of mass starts 40 centimeters above where it ends. So that's the Y center of mass is 0.4 meters. This omega at the bottom, when the meter stick is vertical, plug in my numbers. I'm finding that to be 5.7. Omega is in radians per second. Now, if you want to follow the units through, in the numerator in here, G is in meters per second squared. Y is in meters. In the denominator, the 0.2433 was from adding this stuff in parentheses. So the L squared plus the 0.4 squared. So that's in meters squared. So the meters squared are canceling and leaving us with 1 over second squared, which we in turn take the square root of. So technically I'm getting 1 over seconds. The radians are implied. So radians are not a true unit, and so we can write them or not write them. They're implied in the answer. I tend to write them so I know that I've been thinking in terms of radians and not revolutions. So the angular speed at the bottom, 5.7 radians per second. And again, there's only rotational kinetic energy finally, because this meter stick is rotating around a fixed axis. You have a similar problem on the homework. That is a cylinder or disc around some sort of axis that's not through the center. The approach is similar. The main difference will be finding I nu. The I center of mass will need to be for the cylinder or disc. Conservation of energy, though, works great whenever we're trying to look at an object starting at rest, speeding up, and wanting to relate the height to the speed is why energy works so nicely.